Generalization is a marker for robust mathematical meaning among in-service algebra teachers. My name is Lori Birch, and I am your presenter today. My goals for the presentation are to characterize one mathematical meaning for the cubic identity for binomial expansion, use generalizing actions to operationalize the mathematical meanings construct, and illustrate how generalizing actions can be used as markers for the robustness of a person's mathematical meanings. Algebra is fundamentally the expression of generality in a succinct form so that it can be manipulated. While scholars agree with Mason, teachers, at least in the U.S., often skip the generalizing in favor of the manipulation. In light of this, I used my study to work with two in-service algebra teachers, Brooke and Paul. My goal was to support them to generalize the cubic identity for binomial expansion from a combinatorial and quantitative context, and to support them to engage in generalizing actions to develop their mathematical meaning related to this cubic identity. Correspondingly, the following research questions guided the study. In what generalizing actions did in-service teachers engage as they developed a combinatorial meaning for the cubic identity, and how did their generalizing actions mark progressively robust mathematical meanings? We use the card problem as shown on your screen to support the teachers to generalize the cubic identity, developing a combinatorial meaning for it. Considering the first prompt, how many different 3-card hands are possible, a person may initially consider this to be a 3-slot problem where there are 3 times 3 times 3 or 3 cubed possible 3-card hands. The second prompt in the card problem motivates writing an equivalent statement based on a case breakdown according to the types of hands. Where there are 1, 3, 3, and 1 ways respectively to produce each type of hand, the exponentiated expressions then determine the number of hands within each way. Having introduced a binary distinction of face and non-face cards, the 3 total cards can be written as 1 plus 2. After working multiple cases of this problem for different numbers of cards, the teachers introduced variable notation, generalizing the cubic identity as shown. We then supported the teachers to reason combinatorially about the symbols in the identity so that they could directly connect the a plus b binomials with the expanded polynomial. Continuing the reasoning from the card problem, a plus b cubed can be thought of as 3 selections from a binary choice, where A represents some number of possibilities for one event and B represents some number of possibilities for a second event. The expansion can be produced using a case breakdown. There is only one partial product with exactly 3 A's, and only one with exactly 3 B's. However, there are 3 partial products with exactly 2 A's, and 3 with exactly 1 A. The justification for equivalence in the identity relies on a combinatorial argument for having produced all possible partial products by considering all possible selection scenarios. Before proceeding, I should provide some definitions. Thompson defines mathematical meanings as the space of implications that a current understanding mobilizes. He characterizes the productivity of various meanings according to their potential usefulness for future learning and their contribution to the coherence of existing meanings. Salient features of the combinatorial meaning as I have outlined it entail a sense of completeness based on a combinatorial argument and a direct relationship between the 2 algebraic expressions. I use the term robustness to describe qualitative characteristics within a person's meaning. That is, within a person's space of implications, how strong are the connections, and what is the scope or breadth of a person's meaning. It is the robustness of the teacher's mathematical meanings that I aimed to investigate in this study. Ellis differentiated between statements of generalization, reflection generalizations, and generalizing actions that precede or intercede between formal statements of generalization. Ellis and colleagues have identified 3 types of generalizing actions: relating, forming, and extending. I find this generalizing actions framework to be useful for marking developments in teachers' mathematical meanings. Relating involves identifying similarity between problem situations, which supports a person to develop a web of connected mathematical ideas. Forming involves making a statement of generalization by establishing a regularity or a way of operating, which marks a baseline from which to mobilize their understanding. Extending involves applying an established generalization, which serves to reinforce and broaden the space of implications. I consider the category of extending actions to be particularly useful in marking developments in the robustness of an existing meaning. Within this category, Ellis and colleagues identified 4 types of actions: continuing a way of operating to a new case, removing particular details of a generalization in order to increase its generality, operating on a generalization to extend it to a new case, and transforming a generalization into a new statement of generalization in the process of extending. We hypothesize that in contributing to the development of mathematical meanings, continuing marks the least robust shift, transforming marks the most robust shift, with removing particulars and operating along that spectrum. The teachers were interested in the utility of the identity, specifically for algebra content, and so we provided opportunities for Brooke and Paul to apply their combinatorial meaning, now symbolized in the identity, to various symbolic tasks. I used the remainder of my time to present examples of the ways in which teachers were able to extend their generalization, reinforcing connections within and broadening the scope of the space of implications for their mathematical meaning. We use Paul's work as illustrative of both teachers' work for the initial symbolic problem x squared plus 3y cubed, first making explicit the 3 binomial factors and then enacting the same combinatorial selection to produce the expansion by generating all possible partial products. Moreover, Paul's next simplification included residual indicators that he was attending to combinatorial structure, that is, the 3 ways for selecting the second and third terms. We infer that extending by continuing reinforced Paul's combinatorial meaning for the identity by establishing the reasoning as viable for producing polynomial expansions. Brooke then questioned whether and how the identity could be useful when subtraction was involved, suggesting the problem 7x to the 4th minus 3z squared cubed. This revealed that for Brooke, the identity was particular to binomial sums, not differences. Paul suggested that they treat the difference as the sum of 7x to the 4th and negative 3z squared. Brooke was able to take up Paul's suggestion and again produce the 8 partial products according to selection scenarios. Partial products with all 7x to the 4th factors, with 1 7x to the 4th factor, with 2 7x to the 4th factors, and with 0 7x to the 4th factors. Notice that Brooke's notation becomes more compressed as she represents the 3 factors from 2 selections of 7x to the 4th and the 1 factor with 0 selections of 7x to the 4th. Additionally, Brooke's use of exponents in her simplification indicates continued attention to the combinatorial nature of her meaning by explicitly showing the number of selections of each factor in each term. We infer that in applying her meaning to a binomial difference, Brooke removed the particular constraint within her meaning that limited applicability to binomial sums. We consider this to have marked a marginal expansion in the scope of applicability in that her reasoning now applied to symmetric binomial expansion, regardless of whether or not the problem was presented as a binomial sum. But would the scope of applicability for a combinatorial meaning for the cubic identity allow extensions to asymmetric expansions? When asked to consider the problem x plus a times x plus b times x plus c, Brooke re-recorded her identity in the form of x plus a cubed. She thought for 30 seconds and said,
I'm going to say yes, it works.
Yeah.
But I'm impressed. Even as you were saying it, I was like, that would still work, even if it's not special. Do you want me to do it?
Yeah. Okay. Brooke and Paul then spent more than 2 minutes working on the asymmetric expansion. This extension was not immediately obvious for either of them. At the end of the time, I asked Brooke and Paul to explain their notation.
You went.
So,
For like starting here.
okay, so I wrote x cubed because that's picking all x's. Mm-hmm. And then the second part is picking one x. So I wrote x BC, a xc. I'll start x BC. So I'd chosen x from the first, not the second two. And then a xc, and then a bx.
Okay.
And then it was picking two x's, so that one was xxc, xbx, axx. And then the last one is, typically it's the third thing cubed, but it's picking no x's, so abc. And I accidentally tried to cube it, but that was just because that was what the identity said, and then I was like, that doesn't make sense, because that doesn't make sense. Because it's
awesome.
not AAA, it's ABC, so cubing it didn't help.
Awesome. Okay, so Pavel, how is or can you say a little bit about what we could do from here?
I factored out the x from the, so x cubed, and then factored out the x from the next three terms.
Could you underline the next three terms?
At this point, the witness researcher is underlining the XBC, AXC.
So you said you factored it out. Can you say what you wrote?
BC plus AC plus AB.
I started to do that, but I didn't find that helpful. Because they weren't the same for me.
Yeah.
So.
And then factor out x squared from the next term, so C plus B plus A with the x squared on the outside, plus ABC, and then I changed it so it will be in descending order.
Our initial inference was that both Brooke and Paul extended by operating on their generalization of the cubic identity. That is, to apply the identity to this asymmetric case, they mentally operated on the binomials by treating all three as representing a choice between an x and a not x. This was a significant shift in the robustness of their mathematical meaning because it broadened the scope of their meaning to include applicability to the multiplication of any three binomials. Paul was surprised by this new structure in a way that Brooke was not. He even took a picture of his paper. Additional evidence indicated that for Paul, this asymmetric structure was a new statement of generalization that he could use to directly determine specific asymmetric expansions. An instance of extending by transforming that produced a new structure for asymmetric expansions. Finally, evidence for differences in extending actions and differences in the robustness of Brooke's and Paul's mathematical meanings were found in the directionality of their equivalents. In other words, did their meanings allow them to factor polynomial expansions?
I suppose I've never factored anything that turned into three binomials. Yeah. So I don't think they know how to. I would have to, the remainder theorem, we would have to do P over Q just to get it down to something that we could factor.
Yep.
I mean, it's the numbers that multiply to you find three factors that multiply to 6, but also add to 6 at the same time on the x squared term.
Oh, say that again.
Three factors. So we're looking for three factors. So unlike when we're factoring a quadratic, when we look for two factors that multiply to the last term and add to the middle,
Yep.
we are looking for three factors that will multiply to the last term, but add to the coefficient of x squared. The last double check, like the triple check, was to see if the last piece works too.
Cool.
To close, I will briefly share 3 implications for future research. Our study suggests the need to investigate how generalizing actions contribute to generalization as a cyclic process. This is something that Ellis has referenced but is not articulated in the research literature. Second, Thompson's work has focused on identifying and ranking meanings according to their productivity, particularly for covariation and functions. However, given the differences in the robustness of Brooks and Paul's combinatorial meaning, we see a need to investigate varying degrees of robustness of meanings within a productive meaning, along with how generalizing actions support developments in the robustness of a productive meaning. And finally, how do we support teachers to support their students to develop similarly productive meanings?